You guys have all graphed them. You guys have factored them. You have done a lot of stuff with quadratics. What we do here in Algebra 2 is we start with the graphing, but it's not so much always just what does this graph do, what does it do, it's what do the parts of it mean. And what I try to do with you guys a lot with this stuff is to really get into the understanding of what is exactly going on with all of them. Because as it gets to become more complex, because it will, understanding why certain things do certain things, makes no sense, why certain things happen, is really the most important part of this stuff. Now, as you go through this stuff over the course of today, tomorrow is when we're going to spend most of the time graphing, we're not going to be using the calculator. In quadratic stuff, in this chapter-ish, if you will, there's 8, 9 sections, something like that. There's a ton of word problems thrown in here and there. This is the type of stuff that I do that's both calculator and non-calculator. So there will be times that I'll let you have your big fancy calculator, and times that I'll give you a dummy calculator. Just because of the way that the math works, that we need to understand how certain things occur. So, for example, we have what are called quadratic functions that are written in this format. This is this format that I know that you guys have all worked with because it's the most basic. This is called standard form. Okay? Standard form of a quadratic has a setup where it's ax squared bx plus c, where a, b's, and c's are your coefficients. Your, in front of the x's are your coefficient in front of the x squared, coefficient in front of the x, and the c value is just your constant at the tail end. Now, within these functions, when you guys learn how to graph them, you may or may not recall that these things created what were called parabolas. Does that ring a bell? Now, a parabola is a curve that either goes one of two directions. It's either going to be up, like a cup, or down, like a frown. Okay? Now, within every single one of these graphs, which makes it a parabola, is what we call an axis of symmetry. Okay? This thing called an axis of symmetry probably spelled that wrong, but whatever. The idea of what's called an axis of symmetry means that either half of the curve can fold in on itself. So each point that is on the curve is equidistant to the center that has what we call a symmetric twin. What that means is if there's a point here that's like 4 units away, there's a point here that's 4 units away. If there's a point here that's 7 units away, there's a point on the other side that's 7 away. They have what are symmetric twins. Again, they fold in on each other. Those points are always equidistant to the axis of symmetry because the axis of symmetry goes through the middle of the curve. Okay? Now, when we get into the idea of this idea called an axis of symmetry, since every single quadratic function has one, there's a way to determine where they are located. So, we know parabolas, these quadratics, can either be up like a cup or down like a frown. They still have that axis of symmetry. Now, here's the way to tell what direction things go. And it's a really, really easy way of learning or knowing this. What's your A value? If your A value is positive, you're up like a cup. If your A value is negative, you are down like a frown. It's that quick and easy. If A is positive, we are up like a cup. If A is negative, we're down like a frown. That way, at least when you're doing these graphs, if you know what your A value is, at least you know what direction it's got to go. And the reason why we always like to label that and do stuff like this is because it's very easy to substitute in values and accidentally forget parentheses if you're using negative values and get your curve to flip if you're not careful. So if we know that it's got all points have to be moving upward, if you actually get that one weird one that goes the other way, that means you screwed something up with a sign, with a parenthesis. Okay? So here's what we do. When we have these y equals ax squared plus bx plus c, there's always a way that we set these things up. And I like to follow through doing it the exact same way every single time because it falls into a pattern. And if you fall into a pattern, a lot of you guys like that style of the math where you don't have to think so much about a lot of stuff. So if we get that stuff down pat, being able to think about what things mean later becomes easier. So what we do is this. We always label what's your A, what's your B, and what's your C. After we do that, we always figure out what is the axis of symmetry, our AOS. Now, going back a second ago, we had it. What's the equation of every single vertical line? X equals a number. Okay. Is that going to change for the axis of symmetry, you think? No. So this axis of symmetry is always going to be found at X equals, well, there's a really nice way of figuring this out. It's always going to be located at the opposite of B over 2A. Our axis of symmetry is always going to be located at the opposite of B over 2A. And that will give us the vertical, imaginary dotted vertical line that I always put in there for my axis of symmetry. Now, what else is nice is that every single one of these curves has what's called a vertex. Now, if the vertex, bless you, the vertex in this case, since I'm up like a cup, as you're going through, it's decreasing, 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 hits the vertex, and then it's increasing, increasing, increasing. So that point, if it's up like a cup, would be called a minimum. It's the lowest value. So if this is up like a cup, this is called a minimum. Our vertex, in this case, is a minimum. If it's down like a frown, what do you think the vertex is called? Maximum. Okay? That's where we talk about max mins when we get into stuff like that as well. So if I use a really simple example of y equals x squared plus 6x plus 8. I use this one first, actually it worked out rather clean. The way that I'm always going to go about graphing these things, I'm going to do the same generic setup all the time. So first thing I do is I list out what are my A, B's, and C's. So in this case here, I know that my A value is, what's my A value here? 1. What's your B value? B is 6, and your C value? Since our A value is positive, what direction is this curve going? Up. It's up like a cup. So right away, I'm already going to do this. I'm going to put a dot, and I'm going to label this a min. Because I know that's what it's supposed to do. Just from those 3 values, I know that the generic form of this, the way it's supposed to look, should be like that, where that vertex is at the minimum. It's the lowest point that it's going to be at. Okay? After I do that, I always find my axis of symmetry. So my axis of symmetry, my AOS, or which is x equals the opposite of b over 2a. Well, what's the opposite of 6? Negative 6. And what's 2 times 1? 2. And what's negative 6 divided by 2? Negative 3. So my axis of symmetry is going to be located at the imaginary vertical line of x equals 3. So notice I didn't give you guys any graph paper. Notice how we got done scaling things on our own last unit, didn't we? No. Same basic idea here where we're going to graph these things, but we're going to create our own scale. We're going to work through that. So, and I draw an imaginary dotted line. There's my axis of symmetry. Now, a minute ago, we said that the axis of symmetry is where that vertex is going to lie. Well, that vertex is going to have some ordered pair. Guess what the x value is? It's negative 3. Your vertex always has the x coordinate of your axis of symmetry, no matter what, because it has to. Your axis of symmetry always is the vertex, x coordinate. Now, if I know an x value, what do you think you have to do to find a y value? Yep. Just do direct substitution. So, going back to figuring out our y value, well, what's negative 3 squared? 9. 9. What's 6 times negative 3? Negative 18. What's negative 18 plus 9? What's negative 9 plus 8? So my vertex is at negative 3, negative 1. And we called that vertex, is that a maximum or a minimum? It's a minimum. So I label it. My vertex is at negative 3, negative 1, and it's a minimum. Okay? Now, a minute ago we talked about these things that were called symmetric twins. Symmetric twins are ordered pairs that are equidistant to the axis of symmetry. Well, my axis of symmetry right now is at negative 3. I can either go to negative 4 and substitute in values, or I can go to negative 2 and substitute in values. Does it matter which direction I go? No, I try to make it easier on myself. I'm going to use negative 2. What's negative 2 squared? 4. What's negative 2 times 6? What's negative 12 and 4? Negative 8. What's negative 8 plus 8? 0. So what we're doing here is we're creating ordered pairs for x and y. We already know the vertex is at negative 3, negative 1. If I choose negative 2, we just substituted all that in our heads there, and we got what for our y value? 0. Now here's where it gets interesting. Since how far away is negative 2 from negative 3? 1 away. What's 1 away going the other direction? Negative 4. So at negative 4, it also has to be 0.
And then you can just go with the same scale in that.
No, not necessarily, because it's not going to be up 1 over 1. The slopes aren't going to be the same because it's not quadratic. Or it's not linear. It's got an exponent to it. But now, and that idea though is, what's a really, really easy number to substitute in to this function? 0. What's 0 squared?
0.
What's 6 times 0?
0.
What's 0 plus 0?
0.
What's 0 plus 8?
8.
The idea here is that no matter what, your C value is always going to be your y-intercept. Because if you substitute in zeros for x, you get your y-intercept. Remember that from quick graphs? Same idea. It doesn't change. That's why we did all that. We cover and solve. We did those quick graphs to figure that out. Now, I know then at 0, it has to be here at, let's call that 8. How far away is 0 from our axis of symmetry? It's 3 away, yeah. So go 3 away the other way, you get it at what? Negative 6 and 8. I'm creating symmetric twins to be able to make that curve. By picking the number directly next to your axis of symmetry, you get a quick ordered pair. If it's somewhat close to 0, might as well use 0 because it gives you automatically your y-intercept. When it's written in that standard form, your C value is always your y-intercept. And if however far away that y-intercept is from your axis of symmetry, well, it has to be that far away on the other side as well, because the way of symmetry, the way that things fold in upon each other within these style of curves. Okay? Not too bad, is it?
No. Not yet.
Well, to start with, it's usually not that bad to start with. So the idea here is we label everything out through A, B, and C. We tell whether or not what direction something is going via the A value. If it's positive, it's up like a cup, which means up like a cup. That means your vertex is a minimum. If the A value is negative, your vertex is a maximum. You get that axis of symmetry every single time by using what's called the opposite of B over 2A, and so on and so on. So let's try another one. Same idea. We have y equals 2x squared minus 8x plus 6. Okay. First thing we always do, label A, B, C. What's our A, B, and C in these guys? Good. 2, negative 8, and 6. Up like a cup, down like a frown. like a cup, which means your vertex is located at a minimum. Good. And you got that from just those three pieces. Now, go to your axis of symmetry. Your axis of symmetry is always located at x equals opposite of b over 2a. So, what's opposite of negative 8? Yes, sir. Oh, what is it? 8, very good. And 2 times 2?
4.
8 divided by 4 is? 2. So our axis of symmetry will be located at x equals 2. Which means our vertex has an x coordinate of 2. The vertex always lies on the axis of symmetry. It has to. All right? It has to. It won't work otherwise. So what do you think you have to do then to figure out the y coordinate? Yay! So, 2 squared. 4 times 2.
8.
8. Okay. Negative 8 times 2. Negative 16 plus 8. Negative 8. Negative 8 plus 6. Negative 2. So our vertex is at 2, negative 2. We've already denoted the fact that that vertex has to be a minimum, so I label it now vertex 2, negative 2, and it is a minimum. Now I have ordered pairs. So I have 2, negative 2. Oops, sorry, that's a really bad y. Do I want to use 3 or 1, do you think, to substitute in? Which one would be easier? 1. We'll do that last. I always want to get the very next number on either side of the axis of symmetry, and then I will jump to something that's easy to work with. Okay? So if I use 1, what's 1 squared? What's 1 times 2? What's negative 8 times 1? All right, so we have 2 minus 8 plus 6, 0. So at 1, it is 0. Well, how far away is 1 from your axis of symmetry? 1. Huh? So what's 1 away on the other side then? 3. So then you're
I get what I'm doing.
okay. Now I'll use 0. Not just because it's the next number after 1, but in this case, it's close enough to my axis of symmetry to be able to plot it quickly. What was our C value?
6.
So at 0, it's 6, which means what else has to be at 6? 4. And what we're doing here is we're using symmetric twins. Remember, symmetric twins just means that there are same points on either side of the curve that can fold in upon one another because they're always equidistant to the line that is the axis of symmetry. And there's my curve. Okay. Does this vaguely ring a bell?
Yeah.
Oh, yeah, definitely.
Okay. Same thing happened in Versauer where a lot of people, once they got going, they're like, oh yeah, I can remember this. And it was good, it was good. I mean, as you get going, it's very do this, do this, do this, do this. But what changes ever so slightly is that there are other forms that you can get quadratics in. This is what we call standard form. The other one we're going to talk about today is called vertex form. Okay? This one's called vertex form. Now, this may look somewhat familiar of H's and K's. Remember when we did remember that? What did the H and the K? What did the H and K give you? Horizontal, vertical. But if you had an absolute value graph, that told you where to start it, wasn't it? It was the vertex. What do you think the H and K stands for here again? Horizontal and vertical, and where that means that your H and K is your vertex, which means what is your axis of symmetry? H. Very good. The axis of symmetry is where x equals h. What do you think A tells you? Take a guess. Take a guess. What do you think A stands for again? Exactly. Up like a cup, down like a frown. It does the same thing. The A value tells you direction. A value, if it's positive, again, up like a cup, which makes your vertex A. Then, if it's a negative A, it's down like a frown, which means this is a max. All right. That's where these things go through. Now, what's weird is that you have to remember, when you look at it, x minus h plus k. So if I have y equals -3, x plus 2 minus 1. First, what's your a value? -3. So I know that my a value is -3. Now immediately, down like a frown, which makes your vertex A maximum. So I'm going to write that. I'm going to make this little curve, dot, and a max. That way I know if I substitute some value in and something goes weird, I know that I done goofed. Okay? Yes, sir. Good, didn't want to talk to you. All right. Now here's where it's weird. X plus 2 means what was your h value? -2. It meant it was x minus a negative. See how that goes? So that means your h value, your h and your k, will be at -2 and -1. The k value is always whatever sign it is. The h value is always the opposite. So if it was x minus 4, it would have been h would have been 4. If it's x plus 7, it's -7. Does that make sense? After you do a couple of these h's and k's, that'll start to stick with you. And then that tells me now, where is my axis of symmetry located at? At -2. My axis of symmetry has to be located at x equals -2, because that is the x coordinate that's at the vertex, which means the axis of symmetry is always lying upon it. Okay? So if I start to rough sketch this one, once again, 1, 2. I know it has to move downward because the a value is negative. So I just pick the next number, -1. What's -1 plus 2? 1. -1 plus 2. -1 plus 2. -1 plus 2. All right, you can come now. What's 1 squared? 1. What's 1 times -3? What's -3 minus 1? -4. So here I'm getting my table set again. X's and Y's. My vertex was -2, -1, -1, -4. So if it's at -1, what else has to be at -4? -3. The symmetric twin, since this is 1 away, that's 1 away. And then I would do the exact same thing now with 0. Unfortunately, when I throw 0 into this one, it's not going to be as clean to get my y-intercept because it's written in a different format. Okay? It's written out differently. So what's 0 plus 2? 2. What's 2 squared? 4 times -3? -12 minus 1. There you go. So I know that this has to be at 0, 0 and -13 here. -4 and -13. Yeah. What? So what? You're going to sit there and cross out and count out 13? When you have quadratics, depending upon that a value, the a value is going to show you how wide or how narrow some of those things are going to open. The larger the absolute value of your a value, the tighter the curve. the smaller the absolute value, the wider the curve. So if I have an A value of like -9, it's going to be a real tight curve. So you're not going to want to count out to 50. Just put dot. Tell me what the ordered pair is. The ordered pair is where it's at. And that's how you work these things through. You know, I got 2 turntables and a microphone. Heck, nobody? You guys are all much noise.
Nobody.
Same idea. Same thing. If I have y equals -1/2 times the quantity x plus 3 squared plus 4, I'm going to do the exact same thing. I'm going to go through and label A, H, and K. Where's my axis of symmetry? What direction is it going? Is that vertex going to be a max and min? Max, not max and min, but max or min. They don't occur simultaneously. That'd be really bad. A value is -1/2. So is this up like a cup or down like a frown? So it's down like a frown, which means my vertex is going to be a max. What's your H value? And your K value? 4. So H, -3, K, 4. So our vertex is at -3 and 4. Axis of symmetry is that x equals -3. Now, the axis of symmetry can't have an ordered pair. It's just... Okay. Well, what's the next number?
-2.
What's -2 plus 3?
1.
What's 1 squared?
1.
What's 1 times -1/2? What's -1/2 plus 4? 3.5. So we're doing the same idea. Our first ordered pair is our vertex. Our next ordered pair would have been -2, and what did we say it was at? 3.5?
Yeah.
So if at -2 it's 3.5, what's the other ordered pair that's at 3.5? -4, very good. Remember, equidistant from the axis of symmetry. Now I can make a decision. I can use 1, I can use 0, doesn't really matter. If I use 1, what's 1 plus 3?
4.
4 squared?
16.
16. A -1/2 of that?
8.
Plus 4?
Well,
It'd be -4 then. So at -1, it's at -4. Which means then it also has to be at -5 and -4. Here we have a parabola. Houston, we have a parabola. See what I did there?
Yeah.
It's true. You have to use parabolic curves to go this way. Ellipses, ellipses are all conics. Everything here is quadratic. Yes, sir.
The problem is, I get this, but then like tomorrow we're gonna do something really stuff with it. It's gonna be crazy.
Well, the idea is, do you understand what parts mean?
Yeah.
You understand what parts mean when we get to the crazy stuff, then you understand what we're looking at. Because the idea is not just can we plot and go, but can we figure out distances from a curve going up and down? You shoot something up in the air. What goes up must come down. If you know how high up the maximum height it reaches, well, if it reaches the maximum height, isn't that halfway between where it hits? Where it starts and hits, so you can figure out distances. So it's the idea of how do we utilize these things to go forward.
When it asks, like if a question asks the maximum,
Yeah.
what would be the answer? 4?
To start with, our maximum is just, we're going to call it at our ordered pair. But as we get into the word problems, it could be what is the maximum sales figure?
Right.
So then it would be if you sold 3 pairs of shoes, your dollar, how much money did you make? You made $100. So your maximum profit would be $100. So it's the y value. We'll get to that maybe by the end of the week. We'll talk about how does that work as far as reading the word problem from. Yes, sir. I substituted in -2. Negative. Yeah. Yeah, if -2 plus 3 was 1, 1 squared was 1, 1 times -half is -half plus 3 is equal to -2, or plus 4, whatever it was. It's 3.5 because it was at 4. They're just quick substitutions. Now, I believe I put the problems already on the calendar. It's section 5.1. I know the PDF is there. I want to say it was numbers 20 through 22, and then I forgot. It was 3 of each side. It was 20 through 22, and then it was 27 through 29. So I have 6 graphs. Don't use your graphing calculator, guys. I want you to make sure you get these things done right. It's in section 5.1. I want to say it's page 253, but once you open up the PDF file, just scroll to where it goes through it. Tomorrow, what we're going to talk about is the other form. It's called intercept form, and that's where we're going to talk about terms and zeros, and that's a really, really, really important thing for Algebra 2. It's all about zeros, all about the nothingness. See what I did there? Zeros, nothingness. It's kind of an important thing. Self-deprecating humor.